finite graphs and showed that, well, each of them have algorithms to determine the winning regions for the players and winning strategies for the winning player. And then we started to reap the benefits of, let me just turn off the sound so that we don't get disturbed here. Okay. Then we started to reap the benefits by looking at various logics and essentially reducing the synthesis problem for these logics to a respective game. Now, for LTL, that was fairly direct. We went from the formula to a deterministic parity automaton that accepts the models of the formula, and then simply spread the inputs and outputs into moves for the two players, such that in the resulting parity game, if player 0 wins, then the original formula is realizable. If player 1 wins, then the specification is clear to be unrealizable. Now, because we have to go from an LTL formula to a deterministic automaton, the whole synthesis approach is doubly exponential. Now, for CTL Star, there is an additional level of indirection in here. We go from the CTL Star formula to a tree automaton. It's not me. Okay. Then we need to determine whether or not that the language of the tree automaton is empty or not, because the tree automaton actually accepts all winning strategies, all implementations that satisfy the CTL Star formula. And in order to determine that, we again construct a game, the emptiness game of the tree automaton, which is again a parity game if we start with a parity tree automaton. And again, we have the property that if player 0 wins the parity game, then the original formula is realizable. If player 1 wins, then it's not. Now, a tree automaton works by annotating the tree with states. So we start by labeling the root with the initial state, and then we always apply one of the available transitions to determine the labels of the child nodes. So for example, up here we had P as the initial state, and then there is a transition that says that if you are in state P and you read the empty set as the label, so in this strategy tree we have that no grant is being output, so we have the empty set here. Well, then in the direction of the empty input, we again see a P. In the direction of the input that contains just the R, we see the Q. And correspondingly, now we have a P label here and a Q label there. Now, the tree automaton can be non-deterministic, so it can be that multiple transitions are applicable. We had that situation here where we're in state Q, and we can either move to P in the empty set direction and to Q in the R direction, or we can move to Q in both directions. So, well, it suffices that if you apply one of the two transitions, you end up with a accepting run. So in this example, we applied one transition in one place and another one in the other. So for example, here we are in Q with the empty set. We went to P, Q. Here we are also in Q with a label of the empty set, and we went to Q and Q. Okay, and the whole the run tree is accepting if on every path you have that the acceptance condition is satisfied, which in the case of parity means that the highest color that occurs infinitely often is even. Now, in order to turn the question whether such a accepting run tree exists into a game, we again have two players. The task of player 0 is to pick the transitions, and the task of player 1 is to pick the direction, or in other words, to pick one of the two successor states that are listed in the transition. So for example, we start out with state P, and now player 0 chooses one of the transitions. So in this case, we have two transitions that are in principle applicable. They differ in the label they expect. So this was the transition that was applicable if the label in the tree was empty. And this is the transition that's applicable if the label is the set containing G. So this is the case where the system gives out a grant. This is the situation where it doesn't. And in our tree automaton, we said that, okay, in this case, we go to P in both directions. If we have we go to P in the empty set direction and to Q in the R direction. And here, where we already give out the grant, we just stay in P in both directions. Now, because the player 0 gets to choose between those two transitions, he first of all chooses what the output of the system is going to be, right? Because that's the label on the tree. So if he goes here, then there won't be a grant. If he goes here, then there will be a grant. But he does more. He also chooses in what state the tree automaton should continue if then the next input is either the empty set or it is the set containing a request. So in other words, it not only chooses the output in that step, but also how that output is going to be justified, how it's going to result in a accepting run tree. Now the role of player 1 then is to pick the successor state. So for example, if we're here, then the player 1 could choose to either go to P, meaning it chooses to provide the empty input, or it could choose to move to Q, meaning that it produces the request as an input. And then the game continues accordingly. So if the choice is the P, then we go back to this state. If the choice is the Q, then we go to this state. And as you can see in the game, we have the same colors as in the tree automaton. So if the resulting play is winning for player 0, that means that the corresponding path in the tree would have satisfied the parity condition. And since the player 1 can pick the path that we're checking, it would find the path that wouldn't satisfy the parity condition if such a path existed. All right. So the result is that, yes, please.
Why non-determinism?
So the question is, here we have non-determinism in the tree automaton, while a little bit earlier, actually yesterday we had a long discussion why we actually need to go to the deterministic word automaton rather than going to the non-deterministic automaton. And the issue here was that we were worried about dependency on future inputs, right? Because depending on what the future input is, the non-deterministic automaton might need to go to one state or to another state. So in order to avoid such a dependency on the future input, we went to the deterministic automaton. Now, if you look at the behavior of the tree automaton, if you have a certain prefix of input, then the tree automaton already needs to commit to a particular state. So you can't choose a different state if we happen to go along this path or if we happen to go along that path, because the state is determined already by the prefix that led into that node. So in that sense, even a non-deterministic tree automaton already has this property that common prefixes will lead to the same state of the automaton. So such a confusion as we have it in the non-deterministic word automaton simply can't happen in the tree automaton. But there is no free lunch, obviously. So, and you see that here, the construction of this automaton is doubly exponential, just like the construction of the deterministic word automaton. And in fact, you could, of course, use this algorithm also for the case of LTL. And how would you do that? You would produce a deterministic word automaton. This would immediately give you a tree automaton, but, well, with the same cost. Yeah. So going from this to there will always cost you the double exponential cost. All right. Now,
The construction of the parametric automaton requires to terminize the path automaton.
yes. If you happen to start out with say, LTL. Okay. So we do have the, again, the doubly exponential complexity. The cost arises from going from the formula to the tree automaton, and then, okay, we solve a parity game on the resulting tree automaton, and the complexity here is dominated by the fact that we have a doubly exponential state set. We have an exponential number of colors, so we could in principle also afford to have an exponential parity game solver in the number of colors, but we know that that can be done cheaper. All right, so now the next question, of course, is we really don't want to afford doubly exponential cost. So what can we do about it? Yes, please.
One question. We start with the formula, then we construct a non-deterministic automaton, then we determinize it, right?
In the LTL,
Yeah.
yes.
Each step can cost, in the worst case, exponential blow up, but can this happen twice in a row? So maybe,
Yes.
Yeah, there are examples.
There are examples where the small, sorry, the question was that we have a exponential blow-up translating an LTL formula to a non-deterministic automaton, and then another exponential blow-up to going to the deterministic automaton. Do these two blow-ups accumulate or not? And unfortunately, in the worst case, they do. Okay. So in verification, we of course have the observation that verification with CTL rather than CTL Star is considerably cheaper. So the next interesting question is, if we don't want doubly exponential cost, can we simply go to CTL? And the first answer is yes. If you synthesize from a CTL rather than CTL Star, then the complexity drops from doubly exponential to exponential. And the reason is that translating CTL formulas to tree automata is just single exponential rather than doubly exponential. So now, of course, going to CTL comes with the restriction that every temporal operator needs to be immediately preceded by a path quantifier. And the problem with that is that it suddenly becomes very difficult to specify environment assumptions. So, for example, a typical property that you use in synthesis is this: every request is eventually followed by a grant. And that you can specify in CTL. So you can say always doubly when there's an R that implies that always eventually if there's a request, then always eventually there's a grant. But typically that doesn't hold. You need some assumption on the environment such that if there are infinitely many requests, then there are infinitely many grants or something of that sort. So typically you look at some implication like that, and this is exactly what you can't do in CTL. So I think the observation is that there is no point in specifying that an assumption holds on the entire tree, because the entire tree contains all possible behaviors of the environment, including the ones that aren't fair. So it doesn't help you if you specify that globally something needs to hold, because everything is always there in the tree. So it seems that in order to have a useful specification language for synthesis, CTL isn't really the way to go. So what can we do? And there have been a number of proposals for specification languages with a lower complexity, but that are still useful. And I think the most popular one is GR1. So let's take a look how that works. In GR1, we're back in the linear time world, and we're looking at specifications of the following form. We have a conjunction of assumptions, and we have a conjunction of guarantees. And what we specify is, well, that this conjunction of assumptions implies the conjunction of guarantees. Now, the assumptions and guarantees may be formulas of the following form. It can be initialization properties, that is simply a state formula. Then safety properties of the form that whenever something is true, then something else needs to be true in the next step. So with that, you can describe sort of the state-to-state behavior. And then you have liveness properties of the form infinitely often something. So for example, if you want to say if there are infinitely many requests, then there are infinitely many grants that you can do.
Do you assume that in safety properties and in liveness properties, phi and psi are already state formulas?
Yes, I assume that. The question was, are these state formulas? Yes. For the purposes of the talk here, I'll assume these are state formulas. Okay, now, why are these specifications simpler? Well, the games that result from GR1 formulas are at least comparatively small. You have these safety properties that say that if something is true now, then something else needs to be true in the next state. This leads to an exponential state space because you essentially need to keep track of which of these next conditions are active at any given point. But this is not so bad because sets of assignments can be stored efficiently in data structures like BDDs. In fact, many people argue that this is so easy that we should actually talk about the size of the game graph as the input, and then the game arena is of course considered to be linear. Okay, and then we have liveness properties of this form infinitely often something, and I'll show on the next slide that leads to simple parity games with just 3 colors. So this is also comparatively simple. Overall, that gives you that realizability of GR1 formulas can be checked in exponential time, and as I said, if you consider the size of this graph as the input, then it's actually polynomial. So the slogan is that GR1 synthesis is polynomial time synthesis, which of course is a very, very catchy slogan, which has convinced many people, in particular also in robotics, to use this because it sounds much more feasible than doubly exponential. So briefly about this point that we get parity games with just 3 colors. So we have liveness specifications of this form, infinitely often A1 and infinitely often A2. This is a typo, of course, should imply that infinitely often G1 and infinitely often G2 and so forth. So we have a set of assumptions that if all of them occur infinitely often, then then all of the guarantees happen infinitely often. So this is just meant to give you the structure of the resulting game. We have one loop for every guarantee, and this is embedded in a loop that steps through all the guarantees. So in this first loop, we're waiting for the occurrence of the first guarantee. Now, if the guarantee 1 occurs, then guarantee 2, then guarantee n, and then we return in a loop, and the same thing happens over and over again, then the specification is obviously satisfied because we see all guarantees, in fact, infinitely often. So if that happens, then we visit the highest color to infinitely often. But it doesn't need to happen. It could be that we get stuck at some point not seeing the next guarantee anymore because, well, some assumption might not happen, right? So as we wait for G1, we step through the different assumptions, and if we happen to go through all assumptions infinitely often without actually seeing guarantee G1, then the highest color is 1, and we reject, right? But if at some point we get stuck waiting for the next assumption to become true, then the highest color becomes 0, in which case we accept again, right? So in this way, we reflect this dependency on the assumptions. If the assumption is one of the assumptions is to be blamed for not stepping through our guarantees infinitely often, then we win the game. If actually one of the guarantees is to be blamed because there are all assumptions being satisfied infinitely often without the guarantee to happen, then we lose the game.
I'm surprised why it is not solved in a much simpler way. The much simpler way to say that we know how to reduce generalized bookie to bookie, right, with a counter, which is really what's happening here. And therefore, this is street 1. And street 1 is known to be parity free, and that's the end of the
Well, I mean, what you really want to avoid is having a subset construction over the assumptions.
The standard construction, generalized bookie.
Well, this is what it is, right?
Avoids a subset.
Yeah. I mean, if you use the same trick for street, that's the same thing. I mean, it's. I'm not saying it's ingenious construction, but the result is nice. That you have a specification language that many people argue is useful, and that results in exceptionally simple games. So in particular, you can solve these games with a nested fixed point construction with BDDs. So all this is done fairly efficiently. And this explains why this is popular. Now, there is one...
Mostly it's popular because the title said promise cubic and everybody likes it.
Yes, exactly. Moshe points out that the marketing was incredibly good by just calling this a cubic time problem. And while everybody else talks about the exponentials or doubly exponential, so yes, you find your niche and you're good. But there is, of course, no free lunch, and there is a catch. The catch is that you lose expressiveness. So, for example, you can't directly use an until, obviously. That's syntactically not allowed. Now, that actually occurs. So, for example, this is a property from the AMBA specification, which was done. I mean, you remember the AMBA bus protocol is one of these success stories, and that was done with GR1 synthesis. And the way out is that rather than writing down this property directly in your specification, you describe a monitor that checks whether or not that property is satisfied, and you synthesize that monitor along with the actual design. And then you require that the monitor is successful. So you build this automaton, and you can describe this automaton, if you like, in GR1. But now when you think about it, this pre-synthesis of the monitor, of course, is again doubly exponential. So really, you have cheated yourself a little bit by doing this. However, of course, the nice feature of pre-synthesis is that you can still express what you want. So you're not running into uncircumventable problems. You can do this trick if needed. And when you do this trick, then your specification blows up, and you're no longer so surprised that the synthesis algorithms takes a long time. So in this particular example, you would go and translate the LTL formula into a automaton, and then state with additional requirements that that automaton is now being executed. So we start in the initial state, and whenever we are in state P, and whatever the transition condition is, so not start and not pre, well, then you stay in the state P and so forth. And at the end, you say that the acceptance condition of the automaton is satisfied. So that works, but it means also that the specifications may look a little bit more ugly than you would like them to be, because you have to go from here to there before the synthesis starts. All right. Oh, yes, please.
Why general reactivity? Why 1?
Oh, because you have one such pair, right? You could have multiple pairs and then scale to more complex conditions. All right. So now the third part of our lectures is about bounded synthesis. So the classic algorithms have two major problems. One is the complexity, The other problem is that the implementations that you synthesize tend to be really, really large. That is simply due to the fact that you're building this big game arena, this doubly exponentially large game arena, and then you're finding a memory-less strategy in this big arena, which has the effect that the solution tends to be as large as that arena. So to give you one example, this is the T-Burst 4 component in AMBA, the AMBA bus controller. So the role of this component is to deal with burst transmissions. So you reserve the bus for 4 consecutive transmissions, and correspondingly the controller has this very simple shape where you have these 4 states that count the transmissions, and there's a little bit of setup before that. So this is pretty straightforward. If you use a classic synthesis algorithm, the solution looks like this. So this is still correct, but it has, of course, the problem that you have no idea what's going on. You may use much more memory in simply storing this solution on your chip than needed. And if you subsequently would like to verify that this design is correct, maybe you don't trust your synthesis algorithm, then you sometimes run into big problems. This is, by the way, also a problem in the synthesis competition, where every solution is supposed to be verified by a model checker, but sometimes the synthesis succeeds, but the model checking afterwards does not. So how can we avoid this? Well, the simple idea is we change the problem from the question, is there an implementation that satisfies the specification, to the bounded version, is there an implementation with no more than n states? And of course, by searching through potential values for n, we can minimize the number of states if we like, and so forth. The other effect of that change is that we have a chance to look at the problem from the output perspective. So far, we have only looked at it from the input perspective, that is, what is the complexity in terms of the length of the specification. But now we have this other parameter, the size of the output, that we can also look at in order to determine the complexity. And if you think about it, this is fair, because in verification, we would measure the complexity not just in the size of the formula, but also in the size of the system. In synthesis, so far, we didn't have the chance to do that because we only had the specification. But now we're sort of on level ground with verification. So what happens is that the doubly exponential synthesis problem turns into a NP-complete synthesis problem, with the difference, of course, being that this is in the length of the formula and this is in the bound on the size of the implementation. However, a switch from doubly exponential to NP is significant because we do have very efficient algorithmic techniques for NP problems, and we have very little for doubly exponential problems. Also, many specifications tend to have small solutions, and obviously we are interested in small solutions, because if the only solution is this doubly exponentially large solution, then maybe something is wrong with our design in the first place. Okay, so what do? We again start with the LTL formula, and we translate the LTL formula now in a constraint system, for example, into a SAT problem, and then use a constraint solver to find a solution. Now, the path from the LTL formula to the constraint system involves again an automata construction, but it turns out we don't need to go through deterministic automata. It suffices to go through universal automata, and I'll explain that step in a minute. But one of the nice things about this approach, of course, is that there's no determinization involved. We just have one step. Creating a universal automaton is as easy as creating a non-deterministic automaton, so that is unavoidable. But then the second step, the determinization, is missing. So this would be an instance of a class of algorithms that Moshe and Orna have coined the term sufferless for, because we avoid well, Safra's famous determinization construction in this, which, by the way, I think is a very unfriendly term that appears on so many papers, given that this is such a beautiful construction. But obviously, the algorithmic benefit of not having it is huge. Okay, so what's the story about universal automata? So in the rest of this part, I'll quickly explain what universal automata are. Then we'll build constraint systems. And then I want to say a few more words about what it actually means to build small implementations, because, I mean, minimizing the number of states is, of course, important, but it's certainly not the only thing we want to get small. Okay. So a universal automaton accepts a word if all its runs satisfy the acceptance condition, right? A non-deterministic automaton accepts a word if there is a run that that is accepting. In a universal automaton, we require all runs to be accepting. And I'm going to work with the Kabuki condition. So that means that on all runs, the designated set of states appears only finitely often. How do you get there? It's really simple. So you take your formula, negate the formula, build a non-deterministic automaton, a non-deterministic Büchi automaton that accepts, I mean, that recognizes the complement of the language that you really want, because we negated the formula, right? And then you just look at that automaton and consider it to be a universal Kabuki automaton. So we dualize the acceptance condition, and we dualize the branching mode from there is a run to for all runs, right? So the exactly same algorithms that were invented for the construction of non-deterministic Büchi automata immediately give you universal Kabuki automata. The reason for that is that dualizing the automaton, that is dualizing both the exists to all and the Büchi to Kabuki, complements the language. And of course, the same effect can be done by writing not in front of the logical formula. Okay, so here's an example. This is again our arbiter. So we say that every request 1 is eventually followed by a grant 1. Every request 2 is eventually followed by a grant 2. And mutual exclusion holds. So G1 and G2 are never true at the same time. The universal automaton for this is really simple. So you start in an initial state. And whenever there's a request 1, you go into this rejecting state that waits for grant 1 to happen. So while you don't see grant 1, you cycle in this state. Now, whenever there's a request 2, we go into the red state and correspondingly cycle here until we see a G2. So while there is no G2, we just cycle in this state. Now, the beauty is you can separate these two considerations, because all runs need to be accepting. So this run will handle the property that R1 is followed by G1. This run handles the requirement that R2 will be followed by G2. And since both of them are checked at the same time, we get that both of them must be true. Now there's also a self loop on the initial state, which means that we initiate this check in every step again. So this handles the globally. In every step, we are back in the initial state, and when we see an R1, then we sort of open a new thread that waits for the occurrence of a G1. Okay, so with that, we have a word automaton that checks if a particular trace is satisfying the specification. And now if we have a implementation, then of course we need to apply this word automaton on all possible paths in our implementation. So for example, this would be the simplest possible implementation of the arbiter that I can think of. You start out by giving grant 1, then you completely ignore the input and give out grant 2. You again ignore the input, give out grant 1, and so forth. A really simple solution to the arbiter. Now, if I want to know if this arbiter is correct, then I look at the product between the implementation and my universal automaton, and make sure that every path in this product satisfies the Kabuki condition. So we start in the green state of the universal automaton, and we look at the initial state of the implementation, and then we follow the transitions. So, for example, I mean, no matter what happens, we'll go back to the green state, right? Now, if there's an R1, we'll also go to the blue state. If there's an R2, we'll also go to the red state. So in the case that the environment provides both R1 and R2, then we'll match up this state of the implementation with the green state, the blue state, and the red state. All right? And then as we go from there, well, for example, the green state will again produce a blue state and a red state. So you can see how the product builds up, because both these graphs are being explored simultaneously. Now, in order to determine whether or not this arbitrary implementation is correct, what we'll do is we'll track whether these paths visit the rejecting states, that is the blue state and the red state, infinitely often. So let's just say we count the visits to rejecting states. Then we would start again with the green state and the count 0. Then we go to the blue state and the red state on the transition where the environment provides both R1 and R2. And now the green state still has seen 0 rejecting states, but the blue state, well, has seen itself, so 1, and the red state likewise 1. Now from there, we come back to the blue state, because we haven't seen a G1 yet, right? So we need to stay in the blue state, and therefore our count goes up to 2. The red state here actually doesn't have another red state as successors, because we do have the G2, so we don't need to go back to the red state. However, the green state, of course, generates a new red state. So we come back, and this red state has seen one visit to a rejecting state, namely itself, right? And then we're there. We see a G1, so there's no G2, and therefore, as we come back, also the red state has seen a second visit to the rejecting state. But then we're done, because here we have G2, so we don't need to repeat seeing another red state. Rather, as we go back, it's again the green state that generates a new copy of the red state. So this particular path has seen rejecting states only once. And it turns out now that this situation is stable, right? As I go from here to there and here to there, the numbers won't change anymore. And the idea now is we find this stable situation. We just find this annotation that tells us that actually the visits to the rejecting state, the number of visits to the rejecting states on all paths is going to be finite. Okay, and this is the job of the constraint system. So what the constraint system does is two things. It looks for the implementation, and at the same time, it looks for an annotation of the implementation that proves that the implementation is correct. So we look for such a graph where each state is annotated with a number that indicates the maximal number of visits to rejecting states on a path leading to this state. And this annotation happens to be a complete criterion for determining whether that implementation is correct or not. So the finite state machine is accepted by the universal Kabuki automaton if and only if such a valid annotation exists. Now, how do I describe the existence of both the finite state machine and its annotation? Well, I can do it like this. there might be many ways of describing that. I'll use a subset of the natural numbers as representatives of the states. I have this bound on the number of states, right? So I only need the natural numbers up to this bound. Then I need a labeling that indicates the outputs produced by the finite state machine in that state. So I'll map this set of states into Boolean values, indicating whether a particular output variable is set or not in that state. And finally, I have transitions, which are functions from this finite set of natural numbers back to that finite set of natural numbers. So this takes care of the search for a finite state machines with up to n states. And then the representation of the annotation needs to describe two things. Is a particular state reachable at all in the product graph? So I map the states to a Boolean value that indicates whether or not that state is present. And I have a rejecting bound. So this is again a natural number that indicates for each state of the automaton and state of the finite state machine, what is this bound on the number of visits to rejecting states on paths into that state.
It's not going to be, right now it's unbounded, but it should be bounded by the size of the automaton, right?
Yes, by the, so the question is, I wrote here an unbounded number is,
the cross product.
Exactly, yes. But do I really need the whole set of natural numbers? Of course not. There is a bound. Yeah. And the bound is the product of the two graphs. Okay. Now, of course, this is just a data structure that represents the finite state machine and its annotation. And now I need to give constraints that, well, make sure that this is a valid annotation. And, well, it looks like this. It's very straightforward, but I just wanted to show you an example. So what does it say? Well, first of all, the initial state is present initially. So without loss of generality, I'll say 0 is the initial state of my finite state machine. And I'm saying that the green state here needs to be present in the initial state. Now, for all states T where the green state is present, the following needs to be true. So first of all, the green state also needs to be present on the successor state. So I apply my transition function to the state T, and I make sure that the green state is again present. And this is actually true no matter what the input. So I repeat this 4 times for my 4 possible types of inputs, right? Not R1, not R2, not R1, R2, and so forth. Now, likewise, if I'm in the green state and request 1 is true, then the blue state needs to be present on the successor, right? Because if there's an R1, then I additionally need to transition into the blue state. So that explains sort of the left part of my constraints. Now, the right part deals with the rejection bound. So since G is not a rejecting state, if I transition from G, then the new bound just needs to be greater or equal than the present bound, right? It can't be lower because there is a path that has seen this many visits to rejecting states, but I don't actually need to increase because state G itself was not rejecting. If, however, I'm in the blue state and I move to a successor, then the blue state itself is a rejecting state. So in this case, the new bound on the visits to rejecting states needs to be strictly greater than the present bound on the number of visits to rejecting states. Okay, so this is the constraint system, and it is satisfiable if and only if there exists a finite state machine of this bounded size that is accepted by the universal Kabuki automaton.
Why is it in NP?
Because
This system is exponentially large.
yes, it is. So Moshe's comment was, you're cheating. This is exponentially large, and you're claiming this is in NP. And I was cheating, but on purpose, let's see. Oh, there we are. Here. So NP in the bound, right? Versus what Moshe is observing is that my constraint system is exponential in the specification, because the universal automaton is exponential in the specification. Hence, the constraint system is exponential. But in the bound N, this is actually just, well, quadratic, I think, right? Let's take a look. Right? So it's long in the number of states, right? But that I don't care, because I only measure in the number of states of the solution, and these are actually captured by this quantifier here. I say for all states of the FSM, something needs to hold. And of course, if I don't have a universal quantifier in my logic, then I can roll this out into a big conjunction, but this is still just well, linear in the number of states. Okay.
I have a question.
Yes, please.
So you're cheating. I'm saying that it's NP complete. If you were honest, what would be the complexity? Would it be next complete?
No, I'm of course only cheating. So the question was, what would I say if I were honest? I'm not. So, but NP of course is the honest answer. It's just in the size of the target implementation, right? So the construction is still exponential in the LTL formula, because I need to get from the LTL formula to the universal automaton.
In terms of this argument about the LTL, what would be the complexity of that?
It would be p-space, because I mean there is a verification problem in here, and that is p-space complete. You could imagine just enumerating all my implementations and verifying each of them, and then I would be done with a p-space algorithm. Yes, please.
You said that the problem now is find the specification lesser or equal than the number n. So if you define the problem such that the number n is given in the binary, then you have an NP problem. This would be the
This is what I'm doing here. I'm saying that the NP complexity is in the unary representation of the bound, right? Yeah. Yes, please.
So are you put these constraints into an integer linear programming solver or something like that?
Okay. So your question is, what is the actual solver that I use for this? So first of all, I can give this to an SMT solver if I have if I have the natural numbers, say, or any finite domain that is equipped with order. What we're actually doing is we go to various propositional representations. So the simplest one is to go to SAT. So let me quickly tell you what the options here are. So SAT means that I have a Boolean formula and I just want to know, is this satisfiable or not? QBF allows me to have quantification over Boolean variables, so I can have for all exists in front of that. And DQBF is one step further, where I can bring my quantifiers into a partial order, and I can say for each quantifier on which other quantifiers it will depend on. So if I choose one of these three logics, I get representations that differ in their compactness and in the way they treat things symbolically. So essentially, if I go to SAT, then I don't have much to do symbolically. So for example, my functions need to be represented by accommodation. That is essentially by having a value table for what mappings are in the function and whatnot. If I have QBF, then I can leave some of the functions in my constraint system symbolic, because I can write things like for all x there is a y, which is a way of saying that there is a function f that I can apply to x that namely has the value y. The only restriction with that is that I can only do that if I use this function application just once, because if I would use it for some different value, so say f of z, right? Then if I would write again there is a y and there is a z, then there's no guarantee that these values refer to the same function. They might give me the same value even if they are, I mean, they might give me different values even if I apply them here to the same value. And this problem can be fixed if I have dQBF. So if I have two applications of the same function here, then what I do is I say, okay, let me say for all x1 there's a y1 representing the application of f to x1, and for all x2 there's a y2 representing the application to x2. And now I simply state that if x1 and x2 are the same, then also y1 and y2 need to be the same. So these quantified values here are actually the results of the same function. Okay, so this is an encoding in dQBF of functions with arbitrarily many occurrences, right? And I just need to go from here to there. The drawback is, of course, now I'm in a more compact and more expensive logic. So in principle, you can go to either one of those choices, but it's obviously interesting to see what happens if you make use of more powerful logics. Yes?
QBF solver, you have to do some columnization to extract the function, right?
Yes. So the observation is that if I only have one function application, then I can equivalently replace that function application. But if I'm in this setting, then this doesn't work. So I have to resort back to what I would do in SAT and have, for example, a value table for the function.
Wouldn't it be easier to just introduce variable to encode the model and just fit to a symbolic model checker? Why go through this?
Yeah, this is very close to the SAT solution, because then, I mean, I would need to describe under what circumstances is a transition present, and probably I would introduce a separate Boolean variable for every potential transition. So this is exactly what the SAT encoding does.
But then the model checker takes care of the LTL formula.
Then the model checker takes care of the LTL formula, that is correct. But then I need to solve a model checking problem rather than just a SAT problem. So yeah, it would create a little bit more overhead, but in the end be of course of equivalent result. Now, but the option to go down this road is exciting. So let me quickly look into what happens in our constraint system. So we do have things that occur, functions that occur just with one argument. I mean, just once. So for example, the transition function with the inputs occurs only once in every conjunct, because, well, I either talk about what happens in the next state, or I relate the next state to the present state. Either way, I apply the transition function just once. And this is interesting because this depends on my inputs. So if I avoid listing the transitions explicitly, then I have gained a lot, right? Because there may be many possible inputs. If I have n input variables, then this is an exponential number in n. So this I can already eliminate with the techniques of QBF. Now, the dependency on the state of the finite state machine has two occurrences, right? So for example, here I compare the rejecting bound in the next state with the rejecting bound in the present state, but both of them depend on the state. So this I can't do with QBF. And likewise, the dependency on the state of the automaton occurs twice, because I'm relating the next state of the automaton with the present state of the automaton. So as a result, if I go with SAT, then I can be, well, then I'm explicit in everything. I just need to enumerate everything. If I go to QBF, then I can be symbolic in the inputs, because they occur only once, but I still need to be explicit in the states of the finite state machine and in the states of the automaton. And if I go to dQBF, then I'm symbolic in well, it can in principle be symbolic in everything. So in the inputs, in the states of the finite state machine, and in the states of the automaton. And then, okay, just to have a comparison, I can look at a version that is symbolic in the states of the finite state machine, and one that is also symbolic in the states of the automaton. So the beauty of having things like the synthesis competition is that we have a lot of benchmarks. So we can just run all these options on the benchmarks we have and just see what happens. And well, this is what happens if you run these encodings on the current set of benchmarks in the synthesis competition. So I should preface this with a warning, because I mean this is just a snapshot of how things are today. The benchmarks may change, and in particular the solvers, of course, will change and change their characteristics. But this is very interesting. So for reference, I have two state-of-the-art tools. So this is Acacia, which is a very good tool for realizability checking. And let's see, this one is Eirat's tool. There he is, called Party. And this one, yes. And now let's look at the various encodings. So we have the basic, this is the set solver, the red one. Then we have the input symbolic encoding. So this is QBF. So you see that QBF is, well, at least as good on, than Acacia.
What does it mean? Because Acacia is an unbounded synthesis tool. And now you're
Oh.
running synthesis, bounded synthesis.
Actually, Acacia also uses a bound, just not as a bound in the number of states, but as a way to reduce the liveness condition to a safety condition, right? So it also searches, I mean that bound also corresponds to the size of the transition system. But yeah, I mean, let me explain what this graph actually means. So this is the number of instances solved by the respective tool, and this is the bound in time. So, I mean, obviously, as you give a tool more time, it will solve more benchmarks. But the further to the right your line is, the better you are in this graph. So we simply run the tools and see how many instances they solve, right? This is a first comparison.
The bound synthesis tool by gradually incrementing the
Yes,
bound?
exactly.
I see, okay.
Yeah. Okay, so yeah, so I think first of all, this is a line to keep in mind. Another interesting observation is that if we go to the fully symbolic encoding, things get really terrible, which is completely counterintuitive, because the symbolic encoding is much smaller and gives the solver much more opportunity for doing things better. And the tool, I mean, the DQBF solver could just convert the DQBF problem into a QBF problem, and then it should perform like this, but it doesn't. So, yes, please. No, read it like this. You set a time bound, and then you go here, and you see how many instances are solved up to that time bound. So, okay, so the question is, does all this depend on the set of benchmarks? Obviously, yes. But, I mean, all of them run on the same set of benchmarks. So, as I said, this is a snapshot dependent on so many things that I don't want to enumerate them. But still, it gives you an idea, right? And I think what we can see is that, first of all, the surprise is that QBF outperforms SAT, which I'm pretty sure wouldn't have happened a few years ago. It does make use of the fact that we have a symbolic encoding of the input. And DQBF solvers, which admittedly are still few and are young, right? They simply don't explore their potential yet for this, right? But it will be exciting to see if that curve actually moves in the next years. Now, before Moshe shuts me up, let me quickly say that runtime is one way of looking at things, but I started talking about these things by discussing the size of the implementation. So here's a comparison between the size of the implementation measured in the number of gates in the logical circuit between the bounded synthesis approach and, well, the more traditional approach. And what you see here is the bounded approach is never worse than the traditional approach, and it's orders of magnitude, I mean, at least 1, maybe 2, maybe 3 better than the traditional approach. So what you get here are way simpler, way smaller solutions. And this is partly due to the fact that we're actually searching for the minimal number of states, but it's also partly due to the fact that if your solver has the power to symbolically solve things, then you might get something smaller than just a value table. So this becomes visible if you compare the SAT solution with the input symbolic QBF solution. And here you also see that 1 order of magnitude of reduction is to be expected simply because of the fact that you're looking for solutions symbolically. All right, but more about this then tomorrow. Thank you.